The Instituto Politécnico Nacional welcomes you to the second sessions of the talks entitled High Frequency and Terahertz Devices and Circuits, Perspectives of Emerging and Advanced Technologies, Part 2. Today, we begin at 9 o'clock, and before starting, I will translate the message. El Instituto Politécnico Nacional les da la más cordial bienvenida a la segunda sesión de pláticas tituladas Dispositivos y circuitos de alta frecuencia y terahertz, perspectivas para tecnologías emergentes y avanzadas. Debido a la naturaleza internacional de estas pláticas, estas serán en inglés. Now, Dr. Fontes, please introduce our first speaker. Thank you.
Hi, hello, good morning, everybody. Our first speaker will be the Dr. Ghader Darbandy. Ghader Darbandy is a research associate in the Nanoelectronic Device Modeling Research Group's Competence Center for Nanotechnology and Photonics of THM University of Applied Science, Mittelhessen in Gießen, Germany, since March 2018. From March 2013 to March 2018, he was a postdoctoral researcher in the chair for electron device and integrated circuits in the Institute of Electrical Engineering and Electronics, Department of Electrical and Computer Engineering, Technische University Dresden in Dresden, Germany. He was responsible and working for silicon, nanowire, and organic polymer project within the Center for Advanced Electronics Dresden, Cluster for Excellence. He received the Master and PhD degree in Electrical Engineering from the University of Rovira y Virgili, Tarragona, Spain, in 2009 and 2012, respectively. Now, if the Dr. Ghader Darbandy can start, please. You have the mic with you now.
Yeah, thank you so much for the introduction and the organizers for inviting me to give this talk. I would just like to know, now you see my slides, right?
Yes, we can see it.
And okay, then you can hear properly, then I can start my presentation. Yeah. As you mentioned, my name is Ghader Darbandy, and I am going to talk about single gate, double gate, and gate-all-around transistor, considering nanowires and nanosheet, and showing RF performance. I will also show the DC performance of such devices. Actually, our group, NanoP, it is located in Germany, Gießen, at University of Applied Science, Mittelhessen. And as you can see, the Gießen is actually 70 kilometers north Frankfurt. And this is our campus and our office. And right now I am in my office giving this presentation from our office. And there is around 18,000 students in our university. And our group is mainly developing compact models, which it is input can go to the circuit designers in Verilog code. And we also design, optimize structures, which this is supposed to be input for feedback, which we give to the technology people. And if someone is interested to check the work we are doing within the group, the link is given here. With this introduction, I would like to show the silicon nanowire array this is actually the devices fabricated at NANLab, TU Dresden. This is my previous university. And as you can see, this is the source drain. And we can see parallel array of nanowires. They are putting next to each other. And the reason for putting these nanowires, like bunch of nanowires to each other, the idea is to increase the performance of device per gate width. But the question was regarding this distance between the nanowires. What is the optimum distance, whether it should be 0 or 100 nanometers, for example, and why? So this is the question we are going to answer within this presentation. And again, the idea is to increase the nanowire density. And the reason they are using this nanowire, maybe if we consider this structure, this is the silicon nanowire, oxide, and this is like gate-all-around structure. This kind of device is supposed to be or considered to be like ideal device because of very good channel control. But the problem of such a device is in one single nanowire. The device width is very small, so the derived current is not enough for most of the applications. That is the reason they are putting them in parallel. But again, the question is this one: what is the optimum distance between the nanowires? Because if we consider two nanowires, if they are close to each other, this electrostatics, they see each other, and this electrostatic interaction, which we call it screening effect, we are going to analyze it and show the optimum distance for RF and even for DC performance. With this introduction, I will just show what is the outline of my talk. As I mentioned, I am going to discuss 3 different gate architecture for silicon nanowire FET. We calibrate our simulation to the measurement, DC and AC characteristics. With this kind of simulations, I am going to show details about DC and AC performance of one single nanowire and the performance per gate width. And finally, I will conclude my talk. Okay, regarding the structure, you may all know this is when a single gate transistor, this is the single silicon nanowire phase. As you can see, we have gate and the oxide. This is the nanowire with the diameter of D and the distance between the nanowires. We have the substrate and the gate divided by the number of nanowires, which we call it unit cell. I mean the unit cell, the width, we have one single nanowire. With these 2-3 parameters, I think it will be very easy to follow this presentation. And again, the main point is we want to know what is the optimum D here between the nanowires to get better DC and AC performance. And this is what I mean with this double gate structure. It is the substrate, we have same oxide down and the same gate like this top gate and gate-all-around structure. Again, we are considering this gate-all-around structure as a reference, since this is called like ideal device because of better channel control. And another point is, for example, in this kind of structure, when we are talking about these nanowires parallel to each other, there is electrostatic interaction between them. But for example, here, if we put another such a device next to this one, because of this metal shielding, there is no electrostatic interaction between them. So in this view, we may conclude, okay, this is the best structure to get higher performance, but end of this presentation, we will conclude this is the structure, which should be the last option from not only BC, but from also AC performance point of view. Okay, with this one, this is the device, fabricated device we actually received from the Infineon. The channel length is around 90 nanometer. And we simulated this structure and we compared this is the TCAT result, the line compared with the experimental data. The symbols are showing experimental data for this device. With such an agreement, we can see for transfer, we had the same fitting with the output characteristics. With this kind of simulation and fitting it to the experimental data, we call it kind of TCAT calibration. That means we can say, oh, TCAT simulation, because somehow representing this device and even the technology. And we did the same thing also for this external transit frequency. As we can see, this FT with the VG from the experimental data and compare it to the TCAT simulations. As you can see, depending on the parasitic capacitances, first of all, we can extract the parasitic capacitance for the fabricated device, and we can see this, the parasitic capacitance is around the value which we extracted, and continuing the same procedure for the Fmax, again from the measurement and fitting the TCAT simulations to the experimental data. Again, we are extracting this gate contact, gate resistance, and with this kind of fitting experimental data to the TCAT simulation, what you say, we are claiming the simulation is calibrated to the measurement using DC and AC performance. Now we are using this calibrated TCAT simulation, which it is somehow representing the technology. And we are showing if we fabricate this kind of different devices within the same technology, then what kind of performance, DC, AC performance we can extract. It just was supposed to be my backup slide, but just wanted to show here when I am talking about the gate width, clearly to show what does gate width means. As you can see here, if the gate width is like 12 nanometer here, almost same than nanowire diameter, or if it is 50 or if it is 100 nanometer, this gate width, as you can see, the gate width has influence on the IV characteristics. I will explain why it is happening and what is the consequence. And same thing again with this, the distance between the nanowires. As you can see, depending on the distance between nanowires, we can have very dense nanowires or very, we can increase or decrease the number of nanowires per gate width. With this production, again, what we see here, this is the current per one single nanowire, the transfer characteristics. Okay, this is, we are talking about one single nanowire. If we look at the current from gate-all-around, as it is expected to be like ideal device, and we are seeing very huge current compared to here, for example, I have shown the current for one single gate. As we can see in the single gate transistor, depending on this unit cell, if we decrease the unit cell, or if we decrease the distance between the nanowires, we see that current for one single nanowire is decreasing. So from this point, we may immediately conclude, okay, forget about this kind of structures with this kind of distance, just this is the perfect structure. But that is not the only parameter. We also need to consider another parameter, which is nanowire density. When we are decreasing this unit cell, when we are decreasing the distance between the nanowires, that is right, the current is decreasing. But another parameter is the number of nanowires, which is increasing per gate width. We need to put these two parameters next to each other, then conclude what is happening for DC AC performance of the device per gate, this gate width. And again, the main question is here, what is the optimum distance between the nanowires? And in order to get the answer for this question, based on this simulation, we are showing the current. Again, this is for one single nanowire in a single gate or double gate transistor. This is normalized to the gate-all-around structure. And here we are seeing the unit cell divided by the diameter of the nanowire. What we see here, if we decrease the unit cell from this point up to somewhere like this 4 times the unit cell, you see the current is almost fixed, but starting from this point, we see the critical unit cell is around 4D. This means starting from this point, if the unit cell is, for example, here, if it is 1D, and this means if the distance between nanowires is 0, what is the consequence? This current is almost 50% less. It is the same scenario for the charges. I'm not showing in this presentation, but in the paper, in the previous slide, we showed that in the previous slides, all these figures together with the charge are published in this paper. And again, if we just consider this current per single nanowire, probably we will conclude, forget about this kind of unit cell here because the current is very low. So the best option would be somewhere here. But again, I am going to conclude exactly opposite because of when we are selecting the unit cell, very small unit cell, or let's say the distance between nanowire equals 0, that is right, the current or the charge for one single nanowire is decreasing, but considering the number of nanowires or nanowire density per gate width, this is the conclusion. This is actually the total current per gate width, either double gate or single gate, normalize it to the gate-all-around structure. As we can see, for example, in this case, this is for the double gate structure. If we select this smallest unit cell, which is exactly same than the diameter of the nanowire, so this means the distance between the nanowire is 0. As we can see, we can expect even up to 3 times more current in double gate transistor, or even in the single gate transistor. As you can see, it is again normalized to the gate-all-around structure. Both structures giving better current density compared to the gate-all-around structure, which is supposed to be the ideal structure. Then what I conclude from this slide, I will conclude this is the answer actually for our question. This is the optimum value for the D. So the nanowires, they shouldn't have any distance from each other. Then we can expect this kind of DC characteristics. But what about the AC performance? Whether we would like to have this D as small as possible, or we need to increase this distance between the nanowires. In order to answer this question, again, we can see here, this is the intrinsic gate capacitance with the gate bias. Considering gate-all-around structure, This is what we can see for the gate capacitance. And if we consider double gate structure, again, with the unit cell, we can see what is happening for our gate capacitance. Actually, the gate capacitance is decreasing with the unit cell. And here, if the unit cell is 1D, this means the distance between the nanowire is 0 nanowires. We are getting the gate capacitance is decreasing. But if we also check the transconductance, this is the transconductance for one single nanowire. Again, gate-all-around structure and double gate transistor with different unit cell V. Again, the transconductance is decreasing. And what is the conclusion or the consequence of this unit cell if we check FT, intrinsic transit frequency, for double gate transistor with different unit cell? Surprisingly, we can, not surprisingly, the interesting point is FT is not changing with the unit cell value. This means it doesn't matter what is the distance between the nanowires, it is 0 or it is like 20 times D. We can expect the same FTI, and the reason is actually, this is what I will conclude from here. The distance between the nanowire, it doesn't matter. We will get the same FTI, and the reason is what we saw in the previous slides, this parameter. The transconductance is decreasing with the unit cell. Same thing is happening for the gate capacitance, but both of them, they are decreasing in the same rate. And that is the reason we can expect this FTI, which is almost independent or very weakly dependent on D. Then FT is free of this D, distance between the nanowires. But actually for practical application, we are mainly interested in the external transit frequency. And if we look at the external transit frequency, this is showing the number of nanowires, and this is transconductance and gate, this capacitance, and this is the parasitic capacitances. If we consider one single nanowire, we can see this is going to be attributed, this parasitic capacitance for one single nanowire. But with increasing the number of nanowires, suppose instead of one nanowire, if we put 100 nanowires, this parasitic capacitance is going to be distributed between the nanowires. Then again, from FT external point of view, what is the interesting point? We are interested to increase this number of nanowires as much as possible to make the impact of this parasitic capacitance smaller. Okay. This is up to here. Even from AC performance point of view, we conclude this. We are interested in increasing this number of nanowires and decreasing this distance between the nanowires, and if possible to make it 0. But here, we also see the impact of different structure actually. We have the same nanowire, but if we consider 3 different structure, this gate architecture, and if we check this intrinsic transit frequency, again, what is actually surprising is this single gate structure. As we can see, the single gate structure compared to gate-all-around this structure, it is showing higher FTI and around 30% higher FTI compared to the gate-all-around, which it is supposed to be ideal device. And the reason for this increase is actually weaker gate control in the single gate. And this is actually advantage here to have higher carrier velocity and accordingly higher FTI. How this weak gate control result or leading to this higher carrier velocity, we can see it here. If we look at the quasi-Fermi potential through the channel from source to drain, I can simply show maybe in the next slide where I am showing just, this is the slide I showed at the beginning. We are looking at this red bullet, this point, from source to drain, and we are seeing what is happening for this quasi-Fermi potential. And I have actually selected this point, not only in the single gate, double gate, and gate all around. This is the point far from this gate. In the single gate, we have weaker channel control, and we want to see what is happening with this weaker channel control. Then we can generalize it, because the average control in this structure compared to this structure would be weaker. Then conclusion will work for entire device. Okay. Again, if we look at this quasi-Fermi potential, and if we zoom in, we can see in the single gate transistor, this quasi-Fermi potential is, the slope is more than for gate-all-around structure. And this is because in the gate-all-around structure here, we have much better control. We have more flat Fermi potential here compared to the single gate. And what is the consequence? Consequences is slope for this device single gate is more than, or the gradient of this potential is bigger than the gate-all-around. Bigger gradient of potential means electric field in this device is bigger than gate-all-around, and that is leading for higher carrier velocity.
Excuse me, doctor.
Yes.
You have 5 minutes, please.
Okay, thank you so much. Yeah, I think I will be able to finish in 5 minutes. Thank you. And this is what we see for electron velocity is in the single gate due to the slope and electric field. It is higher than gate-all-around, and this is the reason for higher FTI in single gate transistor. So what is the conclusion so far? I would say for DC performance, I would say this double gate structure is the best device with the nanowires, which they have zero distance between there is a zero distance between the nanowires, and that will lead for actually the nanosheet. Then the conclusion would be to forget about the nanowires if we are going to put them with a zero distance. We can simply put nanosheet, and this is the structure from DC point of view, and this is then would be the single gate transistor, and this should be the last option, the choice from DC performance point of view. And regarding this AC performance, the single gate structure with zero distance between nanowires, which it will lead for nanosheet, would be the best option. Then double gate, and finally this gate-all-around structure. As I mentioned, from both DC and AC performance point of view, as you can see, this should be the last option when we are talking about device performance per gate width. So the question at the beginning was, what about this optimum distance here? We will say, then we could answer this one. It is zero distance, and instead of parallel nanowires, we should use one single nanosheet here. And with this one, I count conclusion. The conclusion is, when we are talking about this parallel nanowires, screening effect is there, and the screening effect is this interaction between the electrostatic. And for this screening effect, not only the distance between the nanowires, but also gate arrangement, different structures play great role. And from RF performance point of view, I would say, the single gate transistor, not with bunch of nanowires, but the nanosheet is the best option to get the best RF performance from such a devices, and this would be the last option. From DC performance point of view, double gate with the nanosheet would be the best option. And another advantage of this nanosheet would be from fabricating point of view. If you are going to fabricate nanosheet instead of nanowires, for the nanowires, this technology people, they need to think about the alignment, the size of the nanowires, their exact distance. But if we just consider nanosheet, the fabrication would be free of all these kind of challenges. And that's all from my side. Thank you for your attention. If any questions, comments, then discuss them.
Thank you, Dr. Darbandy. Congratulations for your excellent presentation. I have a couple of questions.
Yeah.
First, which are the best FT and Fmax reported by FETs based on nanowires so far?
Regarding this, I actually have no idea about the best, because depending on the different structure, different dimensions, or even different, again, the structure and material parameters definitely will expect different, and I don't know what is the state of the art, but the idea of this study was to show, actually, the show at the beginning, the idea was, or the main point was to show here, whether we are going to fabricate this kind of device with parallel array of nanowires, or again, what about the optimum distance between the nanowires? This was the main point I wanted to actually answer. And regarding, again, this question, I would say, what is the state of the art for these nanowires in terms of FT or Fmax?
Okay, thank you. The next question is, have you considered the impact of traps within the oxide in the simulation? Can you comment on that? And two, how different will be the transport in a vertical GA8 from a horizontal GA8?
The first question is regarding whether we consider traps. Actually, we didn't consider traps in the simulations. And sorry, the next question was?
The next question is, how different will be the transport in a vertical GA8 from a horizontal GA8?
This
yes?
is, yeah, okay, I know the question. Again, depending on the structure, I would say, and if it is going, well, let's say in this way, the main point is, I would say, the same thing can be applied for, doesn't matter lateral or vertical stuff. If the question is regarding whether we should use the nanowires or nanosheet, I would say exactly the same thing we can apply for vertical devices, vertical nanowires. But if we are talking about different structure, if we are talking about not, for example, silicon nanowire from another devices like hemp or gallium nitride, I think we need to exactly simulate this same structure. I mean, exactly the same structure with the same material, then only we can show exactly what is happening for the FT. The general conclusion we can apply, we can say, even for vertical nanowires, even for other devices like hemp, nanosheet would be preferable than nanowires. But in order to address exact FT, Fmax, or all other performance, we need to simulate exactly the same structure, then only accurately we can see what is the difference between FT, Fmax, or any other performance.
Thank you for the answer. The next question we have from the chat is, by decreasing the gate control, you may increase the leakage current. Have you analyzed the impact of the leakage gate current on the device performance?
Why you expect lower leakage with the single gate? Because if you talk about the main difference between single gate and gate-all-around, I would say the main advantage of this gate-all-around actually is because of the short channel devices, to control short channel effect. I wouldn't say the leakage current, because the leakage current would be just oxide thickness, and from the oxide, if you are talking about gate leakage, if I can show the structure, I would expect exactly same gate leakage here. If this is the single gate transistor, and we have the same oxide thickness here, and if we compare it with this gate-all-around, if we have exactly the same oxide thickness in gate-all-around and single gate, I would expect exactly, because here in this region, we have same control if we compare the single gate and here, and if you're talking about this gate leakage here, leakage current, I would expect exactly same leakage current. And from opposite side, where we have lower gate control, I wouldn't expect any gate leakage current. If it answers the question.
Okay, thank you. The next question we have from the chat is, have you analyzed the influence of the nanowire diameters?
Actually, we didn't, between this study, I didn't consider different diameters here because it was already too much information for this board. No, we didn't, I analyzed this for different diameters. In this device, in this study, it was around, I think, 12 nanometer, and all the results I have shown here, it is for this one single diameter around 12 nanometer.
Thank you, Doctor. Dr. Eloy, have you any question?
Thank you, Dr. Fontes. Just to say, Dr. Ghader, pretty nice presentation. Just a question. Which are the main issues to be overcome to achieve the ultimate high-frequency performances in these technologies?
In this technology,
Nanowire field effect transistors.
maybe based on the simulation, as I showed here, probably this would be what I would say regarding the best choice of the structure. If again, from here, I would say, I wouldn't go to this structure or gate-all-around structure. This based on the theory, what theory shows, it is showing this single gate structure, and forget about again, bunch of nanowires or parallel nanowires. If for AC performance, I would, we will select this single gate transistor, and again, not nanowire, no parallel nanowires, either in lateral or vertical. This would be the best option. Using, and that is the reason I will not talk about any nanowires if we are talking about this RF performance, even DC, just single gate and nanosheet. This should be the ultimate, I would say, performance we can get from these devices.
Okay. Thank you so much.
Thank you.
We have one last question.
Yeah.
It's from the chat. It say, by silicon sheet, you mean silicon?
Sorry?
The question say this, the silicon sheet, you mean silicon?
Sorry, I cannot get point. What is silicon what?
The silicon sheet, you mean silicon?
Yeah, I don't know if I could understand the question actually.
Okay. Silicon is a two-dimensional version of silicon, is
Okay.
what they say in the chat.
Or if I can check this chat. Or maybe even we can talk. If you can write me the question, we can discuss even bit after the session. Yeah, I think that would be, if we can, you can write me the question, because right now even I cannot find where is this chat to see the questions, and I will answer in the chat actually.
Okay, we will send you the question.
Great, yeah, if you could say that would be very good.
Yes, it's no problem. Okay, any other question, Dr. Eloy?
No, thank you. I think.
Thank you so much for having me. Thanks.
Thank you to you, Dr. Ghader.
Okay, I don't know if they can see the next slide. Yes? Okay, the National Polytechnic Institute, through the Eugenio Mendes de Curro Chairs, grant the present acknowledgement to the Ghader Darbandy for your participation in the webinar High Frequency and Terahertz Device and Circuits, Perspectives on Emerging and Advanced Technologies Part 2, with the conference RF Performance Analysis of Nanowires and Nanosheets in Single Gate, Double Gates, and Gate All-Around FETs, held on November 26 and 27, 2020. Thank you, Dr. Ghader.
Thank you so much for having me.